Our final project looked at predicting flight delays in the U.S. For phase 1 of our project, we focused on understanding what drives flight delays in the U.S. aviation system. We focused on January 2025 because of its unpredictable winter weather, 2 federal holidays, and high travel volume at major hubs. Delays can be caused by weather, airport congestion, or airline-specific issues. We analyzed variables like precipitation type, federal holidays, airline carriers, and airport congestion using Python, Plotly, and scikit-learn. First, our primary dataset came from a database from the Bureau of Transportation Statistics. It contained about 599,000 rows, which gave us a large but manageable sample. We manually selected only the columns that mattered for predicting flight delays. These included things like the flight date, the airline code, the origin airport, the departure delay time, and whether a flight was canceled or diverted. This dataset became our primary source for the whole project because it directly told us the actual delay time for each flight. Anything else we brought in, like weather data or airport rankings, only made sense when it was connected back to this CSV file. For a second dataset, we collected airport congestion information from Wikipedia, specifically the page listing the busiest airports in the U.S. We focused on the large hub and medium hub airport tables since those categories represent the airports that handle the majority of U.S. passenger traffic. To extract the data, we used Beautiful Soup and combined both tables into a single dataset which contained the top 63 busiest airports in the country. This dataset was important because it let us analyze whether airport size and congestion level actually influence delay times. We used the Visual Crossing API to get daily historical weather for Atlanta in January 2025. From the JSON response, we extracted date, precipitation, precipitation type, snow, wind speed, and conditions. Null precipitation values were converted to empty lists for consistency. Finally, we converted the clean data into a CSV file, allowing us to analyze how different weather conditions contributed to delays. When we combined multiple datasets, we found 3 main inconsistencies that we had to fix before running any analysis. The flight dataset stored dates in the format month, day, year with an unnecessary timestamp. This created a problem because our API weather data uses a cleaner year, month, day format, so the two couldn't merge properly. To fix this, we stripped the timestamp and standardized everything using pandas to date time function. Second, a lot of flights in the CSV had no value for delay time. These are flights that were canceled or diverted, so delay time doesn't exist. We replaced missing values with 0, meaning there is no measurable delay time. Finally, in the JSON response, the precipitation type field was sometimes null, which means the day had no rain or snow. But because some rows had lists and the others had nulls, pandas couldn't analyze the column consistently. We fixed this by converting all null values to empty lists. For a CSV dataset, we started by selecting only the columns that were relevant to our analysis, things like flight date, airline carrier, origin airport, and delay time. Next, we cleaned the dataset by fixing the 2 inconsistencies I mentioned on the previous slide. Finally, we renamed all columns to clean, readable names like flight date and delay time, making the dataset much easier to interpret and present. For airport congestion data, we scraped Wikipedia to collect information on the busiest airports in the U.S. We pulled both the large hub and medium hub tables using Beautiful Soup and created 2 separate data frames. To ensure consistency, we applied a unified header list to rename all columns so that both tables shared the same column names. Finally, we merged this HTML dataset with our clean flight CSV using the IATA code as the unique key. This allowed us to attach airport rankings to each flight, and we filled missing airport names or ranks with small airport for flights not included in the top hub lists. For historical weather data, we used the Visual Crossing Weather API to collect daily weather information for Atlanta, Georgia for the entire month of January 2025. We parsed the JSON by iterating through each day, extracting relevant columns such as date, precipitation, precipitation type, snow, wind speed, and general conditions. We converted the parsed data into a data frame and saved it as a CSV file. This dataset allows us to analyze patterns like spikes and delays during snowy and rainy days.
So now moving on to phase 3. Our first insight addressed the question, does precipitation type, whether rain and snow combined, or no precipitation, have an effect on average flight delay times? To answer this, we imported our cleaned airport data and weather data CSVs, and then categorized the precipitation into 4 distinct types and merged the datasets based on flight dates. After grouping by precipitation type, we calculated the mean delay time for each category and created this bar chart visualization you see here. The result table shows that rain and snow combined produced the longest average delays at 21.1 minutes. Rain alone resulted in a 12.3 minute delay, while snow alone caused 11.3 minute delays. Interestingly, flights with no precipitation still averaged 8.3 minutes of delay. We visualized these results in a bar chart, which clearly shows that mixed precipitation conditions have the highest average delay time, followed by rain alone, then snow alone, then clear days. For our second insight, we investigated how average flight delays differ on federal holidays compared to non-holiday dates at ATL. We grouped flights by date and then calculated the average delay time for each day in January 2025. We then flagged federal holidays, specifically New Year's Day on Jan 1st and Martin Luther King Day on Jan 20th, and created this line chart with star markers highlighting those special dates, holidays, so it's easier to spot. As you can see in the visualization, MLK Day shows a notable spike in delay times, while January 1st is not really a notable spike. January 1st had an approximately 7 minutes of average delay, while January 20th experienced a more significant spike at around 18.7 minutes. The chart also reveals that delays vary considerably throughout the month, with peaks around January 5th reaching nearly 30 minutes. Basically, just classifying a day as holiday or non-holiday isn't enough to explain a higher average flight delay time. Our third insight explored how average flight delay times in Jan 2025 compared across major U.S. airline carriers. For this analysis, we grouped our flight data by airline carrier and created a box plot to show the distribution of delay times. This visualization is particularly useful because it shows not just the average delays, but also the median, quartiles, and outliers for each airline carrier, and we made each box plot a different color so that it's easy to differentiate between the carriers. Looking at these results, we can see significant variation across carriers, with Allegiant Air showing the highest mean delay at about 15.3 minutes, followed by Frontier at 14.1 minutes, and Delta at 11.6. What's very interesting here is the range of delays as visualized in the box plots. Budget airlines like Allegiant Air and Frontier show wider IQRs of approximately 21 to 22 minutes, indicating more inconsistent performance and a higher likelihood of long delays. Meanwhile, Hawaiian, Delta, and Alaska appear to have tighter distributions with IQR of about 9 minutes, 12, and 12 minutes respectively, suggesting more reliable on-time performance relative to their competitors. All airlines, though, show extensive outliers on the positive side, with some extreme delays reaching thousands of minutes. For our fourth insight, we applied machine learning techniques to answer how well can precipitation conditions predict flight departure delays at ATL. We built a linear regression model using scikit-learn, incorporating precipitation type as our predictor variables. After creating binary variables for each precipitation category, we split our data into training and testing sets with an 80-20 split and a random state of 42 for reproducibility, with our R-squared value on the training set at 0.0485 and on the test set it was 0.0597. These are very low R-squared values, which indicate precipitation alone does not explain much of the variance in flight delays. The mean absolute error, our model's typical prediction error, is about 24 minutes, which is quite large for flight delays. The scatter plot here shows actual delays versus predicted delays, while actual delays range much more widely, up to more than 1,200 minutes. This tells us that while weather conditions do matter to a very small extent, they're not sufficient on their own to accurately predict flight delays. Other factors must play more significant roles. For our fifth and final insight, we investigated which factors, day of week, day of month, or airport congestion rank, are most important in predicting flight departure delays. As we use a decision tree regressor with scikit-learn's pipeline functionality. We extracted the day of week and day of month from flight dates, incorporated the airport's congestion rank, and used a column transformer to properly scale our numerical features. Our model achieved an R-squared score of 0.035, and the mean absolute error dropped to 19.92 minutes. Even though this R-squared value is still extremely low, explaining only about 3.5% of delay variance, it's important to note that our mean absolute error actually improved slightly compared to the precipitation-based model, dropping from about 24 minutes to about 20. Looking at the feature importance chart, we can see that day of month is the most important predictor, with an importance score of 0.44. Airport congestion rank comes in second at 0.35, and day of week is third at 0.21. Our 5 insights lead to 5 primary conclusions. 1. Precipitation type has significant effect on average flight delay times, with mixed precipitation, rain and snow combined, causing the most severe flight delays and nearly triple the delay of clear weather days, while just rain or just snow have roughly equal moderate impacts. 2. Federal holidays have varying effects on flight delays, with MLK Jr. Day showing significantly elevated delays compared to New Year's Day, signifying that a holiday or non-holiday classification isn't enough to determine if a flight is delayed or not. 3. Budget airline carriers like Allegiant Air and Frontier exhibit wider delay distributions compared to legacy carriers like Delta and Alaska. 4. Precipitation variables alone are weak predictors of specific delay magnitudes, as indicated by very low R-squared scores, demonstrating that delays are primarily driven by factors beyond weather. 5. Day of month is the strongest predictor of flight delays, which surpasses both day of week and flight rank in importance, indicating that monthly travel patterns more significantly influence delay likelihood. These insights can be used by airlines to staff appropriately during high-risk periods like mixed weather days, and passengers can choose carriers based off of reliability needs. So now for our reflection, in this project we learned many concepts and techniques not discussed in class, including 1. Combining multiple datasets from different sources, using pandas merge operations with left joins, matching records based on date columns to create unified datasets for analysis. We also learned how to layer multiple plot elements in Plotly, adding scatter marks on top of line charts by using add scatter, customizing axis ranges, and applying custom color mappings for data in our airline carrier box plots. 3. We learned how to build binary classification features by identifying specific dates and applying conditional logic to label rows as holiday or non-holiday for comparative analysis. We also learned a lot about machine learning using scikit-learn by constructing pipelines that combine pre-processing steps with regression models for model training and evaluation. We learned how to convert categorical features into binary dummy value variables to make them compatible with ML models that require numerical inputs, and we also learned how to extract feature importances from trained decision tree models to understand which variables had the strongest influence on our predictions. Thank you so much.